Okay, so this is what we did last session when we were talking about the electrical field of a ring charge, a uniform ring, a charge that's uniformly distributed in a ring. And we had done the demonstration to find the mathematical expression that that represented that electrical field, and that mathematical expression is the one that we have there on the bottom. Where the electrical field is going to be with regards to certain parameters here that have to do with the radius of the ring, the distance from the center of the ring, and obviously the electrical constant, and lambda, which is also a constant that represents how the charge is being distributed. Okay, so now what we're going to do is a couple of problems using this this expression here. Let me copy paste that onto the other slide. Oh, it's already copy pasted. The slide is here. Moment. And for this, I'm going to need some help from you guys to do the calculations, please. There we go. Okay, so we're going to be doing two problems here. So we want to find the electrical field that's generated by a 1 centimeter radius ring. Radius of the ring is 1 centimeter, that has a uniform charge of 2 microcoulombs, positive, at a distance that's 1 meter perpendicular from the center of the ring. Okay. So let's identify some things here from this situation. And we're going to do that on the next slide. This is the situation. So we want to find the electrical field that's being generated by this ring at a certain distance. So the first thing we need to do is to identify certain things that we need for the expression. So one thing we know is that let's see. There's certain information that we need to be able to use the electrical field expression. Let's see if we can identify these things.
What is the name of the topic?
The topic these are electrical fields, okay, and these are electrical fields on objects that have a defined geometry.
This is the charged ring.
This is a charged ring. Yes, correct. Previously, we talked about point charges. Now, this one is a charged ring, which is basically the same situation as a charged line, but now we're folding up the line into a ring. And so we need to identify certain things from the mathematical expression. So we need to know R, or the value of, in this case, the radius. We need to know also the distance that we're analyzing the situation from. And we also need to know or find lambda. And lambda is going to be the distribution of charge with regards to, in this case, length. Okay, so according to what we see there in the problem, what would be the value of the radius of the ring?
1 centimeter.
1 centimeter, correct. And so R is 1 centimeter, and we need to represent that as meters. So R is 1 centimeter, and this is going to be 0.1 meters. Okay. So the radius of the ring is 1 centimeter, it's 0.1 meters. What's the value of Z? Z is going to be, we're looking, or we want to know the electrical field at a certain point.
1 meter.
It's
1 meter.
That point is from the center of the ring, and that is given as well as, in this case, 1 meter. Okay. And lastly, we need lambda. Now, lambda, again, since we're talking about charges, but the charge is distributed along a linear path, then lambda is going to be the total charge divided onto the length, in this case, that we have, because it's a linear distribution, or it's charged coulombs per meter. So it's going to be the charge divided by the length. In this case, what would we use to find lambda?
The charge of 2 microcoulombs.
The charge is 2 microcoulombs. That's given directly. So in this case, Q is 2 microcoulombs. That's given.
Professor,
Yes.
on the green formula, on the bottom where you put 3 halves.
3 halves.
3 halves, I think yesterday you said it was 2/3.
No, actually, it's
I have it the same way.
no,
Me
it's
too.
it's actually the other way around. I had made a the correction is that it should be 3 divided by 2. So the square root is always going to be there. That's why it's divided by 2. And that correction is actually in the new video upload. So it's 3 halves in the expression. It's 3 halves, and that's also been updated in the PowerPoint. Okay, so if you have your notes, just the 2 is always going to be in the denominator because we've got a square root. So it's going to be 2 on the denominator and 3 on the other.
Is there also the radius system is 0.01?
Oh, it's 1 centimeter, not 10. Good catch there. Javier, thank you. .01 meters. Thank you. And so that's the charge, which would be 2 microcoulombs at 2 times 10 to the minus 6 coulombs. But that charge would be distributed along a certain length. What would be that length in this case?
The diameter.
No,
The 1 meter.
no. Let's look at it this way. We have a certain charge, and the charge is distributed uniformly around the ring.
What's the perimeter?
Would be the perimeter, correct? It's the same situation as the line. But the line was like, let's say that it's horizontal or vertical. Imagine that we grabbed the line and then we made a circle with it. So the charge would be distributed along the complete length, and the complete length of a circle is the perimeter. Okay, so in this case, the length is going to be the perimeter. And how do we calculate the perimeter of a circle? How do we calculate the perimeter of a circle?
The diameter times pi.
The diameter times pi, and the diameter is 2 times r. So the perimeter is going to be 2 times pi divided by multiplied by r. That's going to be the perimeter of the ring, or the I'm sorry, the length of the ring. And so lambda is going to be 2 times pi multiplied by r, that in this case is 0.01 meters. Okay. House turn down for watts. Please do that calculation and give me the value. Okay, house turned on for watts. Please do that calculation and give me the value of lambda. Two times 10 to the minus 6 divided by 2 pi times 0.01.
I got. Isn't this all?
It's gotta be a small number. One recommendation there, if you're using the calculations in your computer, try to, if you're using a PC, try to download the calculator app, and there's a scientific version of that one, and you can do all the notation there.
If we are using a cell phone, do you know of enough that I can use as a scientific calculator?
Is it,
An iPhone?
it's an iPhone, actually, it's already included. It should already be, but if you go to your iPhone,
If you do the horizontal.
yeah. So if you have the calculator and then you just flip it, you're gonna get you're gonna get the scientific.
Because I wanted something that I could like, I don't know, that was, I find that,
More practical.
yeah, something more practical.
I actually haven't downloaded any apps for that, but I do know that there are some scientific calculator apps. Just probably Google that. Just be careful that it's not an app that you need to have a subscription or buy or anything like that. Yeah, so what values did you get?
It's 3.183 times 10 to the minus 5.
3.183.
Yes.
Angels and Power Rangers, please verify.
Okay,
Times 10 to the minus 5.
Yes.
this-
Yeah.
This is gonna be columns divided by meter. I'm always gonna be stressing the units. It's important to identify the units we're talking. And so the rest is gonna be substituting these values into the expression to find the value of E. So now we've got all the parameter of the values we need. We've got R, Z, and lambda. And we already know K is the constant. So bring those into the expression and give me the value. So let's see, Angels do the calculations for this, Power Rangers, and turn on for watts, please verify.
K was 9 times 10 to the 9th, right?
Yeah, let me write that down over here as well. That's always good. Yeah, depending on the text, there's some texts that are very picky about that, and it's 8.999 times 10 to the 9. But for these calculations, it's fine if we round up. So we're going to consider K to be 9 times 10 to the 9 Newton meter divided by coulomb. The electrical constant or coulombs constant. Excuse me? At least for the stuff we're going to be doing, just verify that the angles are that the angle is in degrees, and I think the rest should be fine. And sometimes we're going to be having to calculate angles, and if you have them in radians, it might be problematic. There's a software called MATLAB. It's actually here at CEPI. It's a very expensive software that's used that's a standard also in industry for calculations and for a bunch of things. And actually what I do is I connect to the VPN and I use MATLAB to do these calculations. So I'm using at least $1,000s worth software to do these calculations, and that's overkill. Oh.
I already got it, but I don't know if it's correct.
Oh, give me the value, Andrea, and we'll verify.
No, I think it is incorrect. Sorry.
Oh,
I
okay.
got something very weird, so no.
Don't worry, we can get weird stuff. It doesn't, it might be odd, but let's see, just say you have.
179, 1.79 times 10 to the 10 power.
10 to the 10, let's verify that.
But I don't know if I did it correctly. I mean,
Yeah, let's
it is maybe wrong.
let's verify the calculations. So everybody else also try to, the calculations, remember that these calculations are tricky because we're using a lot of multipliers and negatives in scientific notation. And we need to,
I got a different number.
okay, let's see. Anya, what did you get?
4,295,520,000.
Okay, 4,000.
No,
Oh,
295, 520, and 2 zeros.
and 3 zeros.
I got the same as Giselle. I got as Giselle, but I got 17,996.74.
To the what power, Lisa? Times 10 to the,
Me?
yes,
Yes.
but
I
you
don't know
you
if
didn't, you didn't get a multiplier times 10 to the something?
I'm going to do it again.
Okay,
I got 17,732. Sorry, I know it's 0.78.
okay, let's do this, okay?
I got 7,996.
We're gonna have to take an average of every, let's do this because we need to practice some calculations here. I'm gonna put this in a different color because I'm gonna erase it. Everybody do this calculation. 2 times pi, let's do the numerator first and everybody verify the numerator. 2 times pi times 9 times 10 to the 9. I'm not going to build the units right now, just times 3.18 to the minus 5 times 1, which is z, times 0.1. Let's have this calculation first, everybody.
Professor, it's 0.01, no?
So 0.01, correct, thank you.
Now I got the 17,982.4763.
Okay, and let's use 2 decimals to, so 17,000, can you say that again? Lisa, 17,000?
17,982.4763.
Point,
0.47. I got
So-
that too.
Andrea got that too, over here, can you, can everybody verify just the numerator? Okay,
I got 17,999.
okay, that might depend on the, so for example, this is an interesting exercise, you guys. When we're working with values that are very small, decimals can really affect. So for example, we're okay if we're in the range of 17,000. So the value that Lisette gave is 17,982. You got 17,000.
They use 3.18 and I use
18.3. Yeah.
You still need to divide, right?
Oh, yeah. I'm going step by step because everybody got a different result. Remember, we're learning electricity and magnetism, but we're also learning how to debug something. Everybody got a different results. We need to set a standard. So first we're calculating the numerator. Everybody got the numerator correct. Now, Vienna was mentioning something interesting that I was going to get to. So you got 17,999, but you used one more decimal. So notice how using
Yes,
one more decimal is going to affect the result because we're working with very small values. So actually, the result is also going to be different if you use pi with as pi with the, or if you use 3.14. The range, you should have done around the range of 17,000, but the rest of the value might be a little bit different. Okay, so just be mindful of that. That's the takeaway. If we're working with very small values, they're going to be very sensitive to the decimal. Okay. Okay, so everybody got the numerator correct. Now let's look at the denominator.
Professor, but we use only 2 decimals because I also use the 3
Yeah.
decimal.
Yeah,
Just
let's use 2 decimals
Okay.
for the calculations. Now let's look at the denominator. So the denominator is going to be r squared, which is 0.01 plus z squared, which is 1. The square root of that elevated to the 3. Let's get that value, everybody. And then we're gonna.
I got 1.00015.
Okay, let me just start doing here. That this is a numerator. And this is a denominator. Okay, I'm sorry.
I got 1.00015.
15? Okay, no multiplier, right? Which is very, very close to 1. Why is it very, very close to 1? Because we're elevating 1 to the square, we're elevating 0.01 to the square, and we're adding something very, very small to 1, and then we're calculating the square root and elevating to the 3. So it's kind of like, remember when you guys took calculus and talked about limits and all that? It's really very, very close to 1 what we're calculating. Okay, everybody kind of in sync with that value?
I didn't get 1.0. I got 0.5001.
0.5? Let's check that calculation again, Estrella. So it's 0.01 to the square plus 1.
Oh, it's because I didn't to the square?
It's to the square.
Square root, it's because in the formula is to the 3 halves, so I did it like that.
So that's another thing. It's very important to do the operations from the inside out. So first we're calculating the part that's inside. So it's 0.01 to the square plus 1. Once we get that, we calculate the square root and then we elevate to the 3.
Okay, it's because I followed the formula and it doesn't have square root, and I put in the calculator that to the 3 halves. So I'm going to do it better with the square root.
Oh, but if you do 3 halves and square root, it should be the same. But I'm not sure how the calculator is interpreting that. But yeah.
Is there,
Uh-huh.
I do it like that and I got 17,974. I don't know why.
For the numerator?
No, like the answer, and I already did it like 3 times.
No, but let's go step by step. First, I think everybody's agreed on the numerator, okay? And now I want everybody for us to be agreed on the denominator before we do the next calculation.
Andrea sent me her answer, and I think it's correct, because the denominator is 1, so
Yeah,
I think Andrea's answer is correct.
yeah, I think I'm not saying it's not. I just want, because since we have gotten different results, I just want us to verify. But yeah, it's gonna be close to 1,700, 900 and whatever. But so are we clear on the denominator then, everybody?
Yes.
And so if we do the calculation now, well, I think that the electrical field is going to be, just divide these 2 numbers, it's going to be very close to 1,700 something. Just give me the do the division with all the decimals with the 0.015, just to be
17,979.7730.
Yes, I got the same.
okay in a moment. 1,700 979.7730. I'm gonna leave it at 3 newtons divided by Coulomb. So that's a 17,900, close to 18,000 newtons Coulomb electrical field.
How will it look like in scientific notation?
This should be, there's more than one way to represent that in scientific notation, so this would be,
Like
Uh,
1.79?
it could be 1.79, no, 1.7979 times 10 to the 4. That could be one way of doing it, or another way of doing it, if we want to, there's many ways to represent the same magnitude. It could also be 17.97 times 10 to the 3. And why did I put the 10 to the 3 instead of the 10 to the 4, just as an example?
The point was.
Yeah, was moved to the other side, but another way of representing the same magnitude is to say that this is equivalent to 17.97 kilo. Kilonewtons divided by Coulomb. Why am I putting this example? Because of the magnitude. If I tell you 17,979, that's a large number. If I say 17.97 times 10 to the 3, well, mentally you might say that's a large number. But if I say it's 17.9 kilo something, you know that kilo means large. If I say it's 17.9 mega something, it means that it's even larger. Okay, so that's why the multipliers, the kilo, mega, etc., or when we're talking about small things, the micro, nano, pico are also important because it gives us a kind of a sense of magnitude. So those would be a few ways to represent that. Depending on the settings on your calculator, and it's a long time since I've used a calculator, a physical calculator like those. I didn't even know people still have those. So Juan Ignacio, you're mentioning that you have that since high school or something like that?
Yeah, this one.
Yeah.
Wow.
I didn't even know that the students still use calculator. I'm glad.
Or
What
one
can
of
you-
No. It's a thing that I didn't mean it that way. I meant that there's been a tendency in teaching math for students not to do calculations. So that's kind of a tendency in secondary school and high school. So when I was in school, you had to carry your calculator. In secondary school, you had to carry your calculator, and even the scientific calculators, which were these large calculators that did, no, even larger than that, because they had large screens to do graphs, the large Texas Instruments ones. So that was kind of the thing when I was in high school. But I've heard about this tendency where they don't want students to do calculations, and it's just like mathematical notation like that. So I don't know if that's why I was
At
surprised.
least in settings, you also need to have your calculator every day. If you take physics or chemistry or something.
In
like
math,
that.
maybe they don't let you use your calculator.
Physics or.
You have to have,
chemistry.
I
In calculus, you don't use calculator because they want you to
do the
learn.
procedures.
Yes.
I actually personally, I think it's a good practice for you guys to know how to use a calculator, because you don't know when you're gonna have to do a calculation. Where we've gotten so used to using computers that things that are more like common sense calculations, I'm concerned that engineers don't know how to do that. So I think it is a good practice for students to use calculators. But again, there's been all these like sort of tendencies in teaching math and physics that students shouldn't do calculations. They should be, I don't know, doing spiritual stuff in math. I don't even want to get into my opinions on that, but I do think it's important for you guys. So I was kind of surprised to see you guys with your calculators. That's not something I usually see.
My math teachers in high school asked us for a calculator.
That's a good practice.
Sometimes we didn't use it, but they like teach us.
Well, at least to know how to use it. So it's a good practice. This is ancient history for you guys. It's totally and completely ancient history. and I feel really old. I was talking to one of my friends. We're also classmates from, we both studied at the same time here at the cybernetic electronics. And he was telling me, because of a birthday that came up, he's like, do you realize how old we are? He told me. And I'm like, yeah, we're both 47. I'm like, do you realize, he told me, do you realize that the 1990s are for you guys equivalent to the 1960s for us? So I look back at the 1960s, the music, the movies and all that, and it's like, wow, that's old. It's really old and dated. And he was telling me, do you realize that the 1990s for you guys are like the 60s for us? So you look back at the 1990s that were 30 years ago, or even the 80s that were 40 years ago, and that's like ancient history for you guys. Not ancient history, but there are things over there that you probably don't understand that we did. But something that I even remember using, do you guys, are you guys familiar with what's called the calculus ruler? Okay, so you guys use your calculators, and you might say, well, that's kind of thing having to do with calculations there. Before electronic calculators, you can Google this. There was this thing called the calculus ruler. In Spanish, I think it's regla de cálculo. It was physically a ruler. So it was physically like a ruler where you did calculations there. So for example, right now, if I ask you, calculate the logarithm of 2, just grab your calculator, put a 2, press enter, and you get that. Before, you literally had a board that you had to move the board around, and it gave you the logarithm of 2. Everything you needed to do was in a physical stick that you carried around, and you brought the stick out and you did that. It was probably, if maybe, well, your parents are much younger than me, probably. But maybe if your parents or grandparents or uncles or aunts or whatever are studied engineering or even studied anything, or maybe architecture or anything like that, or then are older, you'll probably ask them, and maybe they even have their calculus rulers. He's got that. And it was interesting because if you wanted to do a calculation, you literally had to move like a. You guys know what an abacus is, right?
That was what you were going to say.
The abacus? Well, I'm not that old. I'm not as old as the abacus. I'm not. We didn't do things on tablets like Moses and all that. I'm not that old. But we didn't use the abacus. But I remember having used the ruler. And the other thing, for example, if I ask you to do an arithmetic operation, you probably know how to do most arithmetic operations. But for example, I don't know if they taught you in high school or secondary school or primary school. Do any of you know how to calculate a square root?
Yes.
You have been taught. That's, for example, that was a kind of a lost thing because they stopped teaching that. My mother is a very, very old school teacher, and she knows how to calculate a square root. I don't remember how to do that. It's kind of like a relatively useless ability. But yeah, I didn't know they still teach that. So they taught you how to calculate the square root. But you don't use that for anything. But
the teachers here in Cetis, especially the calculus teacher I had in high school here in Cetis, Lucia, actually teaches a lot of those like useless, but she says like, no, you have to learn it because it's basic math, like yes, calculating the square roots. I mean, I already know how, but that sort of things, or for example, like calculating the sine, cosine, or something. She also taught that, even if you could just do it in a calculator.
and yeah, and those are kind of lost skills. And well, I was going to pause the recording, but I don't mind if it's recorded or not. But they're kind of lost skills. Where you're like, why would I need know how to calculate a square root. I don't know. But
So that you understand what you're doing.
well, one thing is that to understand where things come from, that's important. The other is what I call mental push-ups. And for people who train, you understand that if you want to do a competition, you need to first prepare your body for that. The mind is the same thing. So doing some things, I think I mentioned to you guys that I always tear up my notes before a class because I want to remember how to do the integrals. And that's kind of mental stuff. But the other thing is that if we have World War IV tomorrow because Russia invaded Ukraine and something happens, we don't know if we're going to need any of these skills when technology goes away. I'm going to give you some mental gum, all of you. You guys know how to use a mouse in your computers, right? What if I took away your mouse? What if I took away your mouse and any sort of way of graphically interacting with your computer? Would you be able to do stuff with your computer and find things that
Basic.
We learn how to do programming.
there's machine code.
Pero was it mouse? No, you can use
No.
a keyboard.
There's a way, there's a command
Yes,
line.
you
where-
can use the keyboard, but because he said that we learned programming.
But finding a file, moving around without the mouse. I come from a generation where Windows 95, I think, and other Windows were new and mouse interfaces were new. I played video games that were text video games. So literally the video game was a black screen where you are walking here and you found someone. What do you want to say? I want to say hello, enter. He said hello back. Now what you want to do? I want to fight, enter. He has brought out his sword or her sword. I brought out my sword, enter. And it's a black screen. That was a video game. That was a video game. There was no literal video interaction. Okay. And so that's another skill. There's a bunch of skills.
The video part of the game.
Did not exist. It was the only video part of the game was the fact that there was a screen there. So yeah, there's a lot of things. I'm mentioning this because when I was walking back from the bathroom, there were some students talking about World War IV. That I have this ability that's a useless ability in most cases, but if Juan Ignacio whispers something to Javier right now, and I'm talking to you guys, I'm gonna hear that, and I'm gonna register that. I have this thing, excuse me?
It's not.
It should be useless. It's
You
a,
are like the dental card.
what's her name?
I don't know.
Yeah,
I don't know.
I just have it and I won't forget. But
Yeah.
You World War III happened?
it's 3, actually, yeah, it's 3. I jumped one. But I have that ability, and I was walking and they were talking about World War III. And Einstein has a phrase that he said, I think World War III or World War IV was going to be fought with sticks, meaning that the world was going to get to a point where it was going to be totally annihilated and any sort of technology was going to disappear. So anything that we use right now as technology was going to be completely useless. So the only way we could fight each other was going to be with sticks. That was the point we were going to get to. So yeah, there's a bunch of things that you might know that you might think are useless, but when let's hope World War III doesn't happen, but after maybe one of those drastic situations, you might not know if using a square root is going to help you learn what time it is. So I don't know, they're not necessarily completely useless skills and abilities. Okay, that was an interesting discussion. Let's hope World War III doesn't happen soon. But things are escalating, so we're living in a very weird time right now. Okay, back to more mundane things. Questions with these calculations. Remember, we're going long, so if you guys need to go to the bathroom, yes, go to the bathroom, stand up a little bit, anything like that, please go ahead. Over at home, I hope you guys are at least awake, and remember that you guys can also jump in and it's welcome. That's a weird thing about this sort of hybrid model, that's a weird thing about the interactions at home and over here in the classroom. Okay. Okay, I am gonna copy this value because we're gonna need it for the next. We're gonna need it for the next problem.
So is it that if it's close to 1800 is correct, right?
Yeah, when we're talking about very large magnitudes, because this is a large magnitude, it's 17 kilonewtons coulomb. Very close, 17.97 kilonewtons coulomb. If we round it up to 18,000, it would be okay. I'm not going to be that extremely picky about any calculations you guys do on problems or for homeworks or exams, as long as the procedure is correct and the range is correct. So again, if you use 3 decimals, it'll probably going to be different if you use 2 or 1. Okay, so I understand that. If you would have gotten something completely out of the range, at least in the first 2 digits, then that would be a concern. I'm going to copy that value because we're going to need it for the next problem. Just give me a moment. Okay, so we're going to jump to the next one. And so in the next, I'm going to clear this, and remember that all of this is going to be updated on the PowerPoint. Okay. Okay, now, so problem number 2. For problem number 2, we have that we want to find the electrical force now between the ring charge of problem number 1, so the previous one that we have. Now we are going to be placing -3 microcoulomb charge here. So now we're going to place a charge here. This is a negative charge. That's a 3 microcoulomb charge where we have analyzed the electrical field. And so if we place a charge there, and place the charge here, this 3 microcoulomb charge, we know that the electrical field, because the ring charge is positive, is going this way. And so there's going to be a force. In this case, is the force going to be of attraction or repulsion in the charge?
Attraction.
It's going to be attraction, correct? Because in the previous problem, the ring, it said that the charge was positive. So the ring has a positive charge. This has a negative one. So there's going to be an attraction force going downwards. I'm going to check my color coding here. Very picky about colors. So we're going to have an electrical force that's going to be an attraction force. That's going to be going downwards. I'm going to call this FQ. in this case, Q is going to be equal to 3 minus 3 microcoulombs. And remember that we're putting the sign here just as a reference. We don't use the sign for the calculations because it might be misleading. And the force FQ. Oh, everything okay, Ricardo?
Ay, perdón. I didn't realize I was.
Don't worry, let's just mute. Let's just do a mute there. But are you okay?
Sorry, yeah, I made that sound because I remember I have to do my sister's carpool.
Yeah, don't worry, don't worry, don't worry. Been there. Okay, thank you.
Sorry.
No worries. FQ is going to be equal to, or the force on the charge, remembering that if we have the electrical field is going to be equal to the force on the charge per unit charge, and from this expression we know that the force on the charge is going to be the electrical field that's being exerted multiplied by the charge. And so FQ is going to be equal to E multiplied by Q, and so this is going to be equal to the 17,000. I'm going to use the value that we had over there. Multiplied by the 3 times 10 to the minus 6 coulombs. And so what would the force be in this case? The force on Q, what would be the magnitude of the force on the charge Q?
I got minus 0.053
Okay, give me a moment there, Estrella.
newtons.
Could you say that again, Estrella, please?
Minus 0.0539.
Okay, now these would be newtons. And just remember one thing, and I'm going to be stressing this. Right now, we're calculating the magnitude of the force. So we're only interested in the value. We don't put the minus in the calculations. Okay, so we're only interested in when we use the formulas for the force or Coulomb's law, we're not going to include the signs because they can be misleading. Right now, we're only interested in the magnitude, and the magnitude is 0.0539. Can we verify that value?
Yes,
Did we
I
get
got the
that?
same.
Okay, good, cool. Good. Okay, good. So we got that one there. Okay. Okay, questions with this one? Okay. Let's save the screenshot. It's really interesting that you guys are living history. I don't know what's going to happen with your kids or what their situation is going to be with your kids, but let's assume that things get back to normal after the pandemic. So things get back to normal and all this social distancing. We don't have to do it. Imagine you having to explain to your kids that you took classes like this and that you took classes from your house and that you had to use Zoom and all that.
We couldn't see our friends for like a year.
See your friends for like a year.
It's gonna be an excuse for not letting them go out.
That's gonna be, wow, that's
Yes,
good. That's
like,
good.
Just
And
to
If and you've been planning about this, so yeah, if I couldn't go out, you're not gonna be able to go. Yeah. Yeah, it's gonna be great. And on the other hand, imagine the kids right now, when they go back, it's gonna be weird for them, how they're gonna be interacting. We were, my wife and I were so stressed because my daughter got a 6 in her spelling exam. And she didn't understand what that meant. She was actually very happy that she got a 6. And some of her other class kids.
She got 6 in her exam.
in her exam. It's the third exam she's had in her life. And it's a spelling exam in English. And she got a 6 in the exam. She's 6 years old and she didn't understand that. And she's like, well, at least I didn't get a 1 because some of her classmates did get lower grades. And we were talking about that. These kids have never experienced like having an exam face to face. And that's really weird.
Our grandchildren are gonna have their children.
Well, let's hope we don't go there, but it's really concerning because how these kids are gonna go to primary school and then from primary school, how they're gonna go to secondary school and all that, and how it's gonna generate a trickle effect on education. It's gonna be interesting to see what happens in a few years.
For example, there's kids that learn how to read or basic things like that, right?
Yeah,
In Zoom, imagine their life.
Well, it's actually what you're saying, Giselle. It isn't that far off. I mean, we've lived it and seen it with my daughter and her classmates. The children in Zoom, it's really frustrating for them to learn. It's really frustrating for them, and you see that it's frustrating for them and it's frustrating for the parents as well. It's really complicated.
Or for the cousins that have to
Yeah,
help them. I had to help my little cousin and she cried.
I know, it's really frustrating.
It's hard to teach children how to pronunciate also because they said English was the best son. It's like you're trying to explain them how to.
That's another thing.
pronounce and all that.
That's actually another thing that's a very mechanical thing, but it's actually true. With the children, when you're trying to enunciate and they've got the masks on, it's complicated. It's not the same. Even that, it's a very mechanical thing of having a mask on. It's really an issue. And it's also in English. And so they gave us an explanation of how the primary school was going to be. And it was funny because they're going to teach the kid, where I have my daughter, they're going to teach the kids Mandarin, and they're going to teach them financial whatever. And my wife and I were very excited with, oh, she's going to learn Mandarin, and like we're going to be able to tell the kids of other parents, the parents of other kids, that our daughter knows Mandarin. So whoopsie do. And I told my daughter, you're going to learn Mandarin. That's so exciting. You're going to learn Mandarin. You're going to learn Chinese. And she's like, I don't want to learn Chinese. I don't want to learn English. I don't want to learn another language. I'm struggling with English as it is. So I don't want to learn Mandarin. So yeah, and doing that via Zoom, I have no idea how that can be efficient, but let's hope that they can come back soon. Okay, let's look at the last situation we're going to be talking about in this section, which has to do with, now we're going to be talking about a disk that has an electrical charge. And again, these are situations that actually happen that have to do with real life situations. We've got a company right next door, which is Skyworks, that basically does semiconductors. And one of the basic things when you do a semiconductor, you can actually Google this, but there are things called wafers. What is a wafer? Does somebody know what the word wafer means? What is a wafer?
It's not a cookie.
A wafer can, you've heard the term wafer talking about cookies.
Or wafer can be like something to feel.
No, that's a
wafer.
That's a wafer. But the wafer is something it's something usually circular. That's why it's related to cookies. Something usually circular that's very flat. And so yeah, that's why wafers are related to cookies. That's the word in Spanish, actually. And so actually semiconductors, which are the chips that we use in most any electronic devices, these are done in wafers. So it's actually like if you've seen if you've gone to the supermarket and bought ham, but not ham that's in a package, that ham that you cut, and there's this cylinder where you cut the ham. That's literally what happens with semiconductors. A semiconductor is this very large lingot that kind of looks like a ham. It's like a tube. And they cut that like a ham, and the little discs that are created, those are called wafers, and that's where they print out the electrical circuits. That's what they do here in Skyworks. And so if we're working with electrical things in a disk, any sort of electrical or magnetic fields are going to be important to know. So in this case, the electrical field of a disk is going to be important, the magnetic field as well. But right now, talking about a disk, a few things to mention here. The situation we're going to be looking at is we're going to have a disk that has a certain radius, R. It's a disk that's of a certain length. And we're going to be looking at a point that's located from the center of the disk, and we want to know what the electrical field in that point is. Now, in the previous, the disk has a uniform charge around it as well. But in the previous examples, they were linear. So it was a line or a circumference. In the end, it was a line, it was linear. The charge was distributed linearly, meaning that I had a certain amount of charge per meter. Here it's going to be different because the charge is going to be distributed in an area. So it's going to be the charge by meter squared or by area. And that gives us another value here, or another constant that's important to think about. And that's called lambda. Lambda was the sigma, I'm sorry. Sigma is going to be the distribution of charge per area. So for example, in this case, sigma, if this disk has a charge Q, sigma is going to be Q divided by the area. In this case, the area of a disk. Right now we're talking about a disk, but it could be a square, it could be a rectangle, it could be any value. And so the charge is going to be distributed uniformly around a certain area. So let's talk about how we could get this, how we could find this expression. The procedure is going to be very similar to the ones we did previously. And again, as I mentioned before, I'm going to be doing this here, but there's going to be a separate video of this explanation in the YouTube channel. Okay. So the way we're going to analyze this is similar to the way we analyzed the previous situations. And so now what's going to be happening is that we are going to be looking at a certain, in the previous examples, we looked at a point charge and saw how that point charge differential affected how that point charge affected the whole, how that point charge was taken as a differential point, and we analyzed that electrical field, and then we added them up, and that gave us the whole electrical field. Well, here it's going to be similar, but in this case, we're going to be looking at this as if it were a ring of charge. And so what's going to be happening here is that we are going to be having an electrical field, okay, that's going this way. Well, actually, I'm sorry. This is going to be the electrical field that we know is going this way because we already analyzed the electrical field of a ring. In the previous example, we already know the expression for the electrical field of a ring. Okay. That electrical field, we know it's going to be going upwards. Okay. We already know that. The electrical field of a ring is given by a certain parameters, and we already have that. We actually already have that expression. Go back a few slides. Just give me a moment. We copy paste that from the previous slide, just so we have it here as a reference. Give me a moment. Okay, so I'm just gonna put that as a reference. That is the, on this side. This is the expression for the electrical field of a ring. Okay, we had already previously found this one. Okay. And given a certain ring of a certain radius, that was the expression that we had for the electrical field. Now let's assume that the way we comprise a ring is that it's an infinite number of the way we comprise a disk is that it's an infinite number of rings that we're adding up. So we're going to be based on this expression here. But we're going to change a few things. And so in the original representation, we had a ring that had a certain radius. Right now, we're going to be defining a differential that we're going to be calling dx that's going to be moving from 0 to the length of the disk. And so now we're going to substitute r for x, which is going to be this variable that we're going to be having. And instead of having lambda, we are going to be working with sigma. So those are going to be the main changes that we're going to be doing to the expression to be able to do the differential. And so let's organize this. Okay. Okay, so first off, we have sigma. And so sigma is going to be the charge or the differential of the charge divided by the differential of the superficial area. Okay. Now, the area is, well, let's represent it this way. It's going to be the charge per unit area. And in this case, if I'm thinking about a ring or a certain distance x, that area is going to be it's going to be pi multiplied by the radius. And in this case, the radius squared is going to be x squared. Okay, it's this distance here. So I'm going to be going from 0 to the length of the ring. And so if the length is x, the area that I'm going to be covering is pi times x squared. From this, we are going to have that Q equals sigma pi x squared. And so the differential of Q is going to be 2 pi sigma x times dx, which is actually the differential. Okay. And so we're going to be doing the analysis similar to the other ones. Okay. We're looking for the differential of E. I'm gonna be grabbing a small representation here of the charge here. And I'm gonna be calling it this dE dQ. The procedure is exactly the same as we've done it before. We know that the horizontals are gonna eliminate and we're just gonna be left with the vertical. So dE, I'm sorry. Is gonna be equal to, rather the, let's do it with the integral. The electrical field is gonna be the integral of all of the dE's. And we know that the dE's is gonna be the dE dQ multiplied by the sine of alpha. The procedure is exactly the same way we've done it before. If we look at the triangle here, we've got alpha, z, x, and r equals the square root of x squared plus z squared. Then we know that the sine of alpha is equal to z divided by r. So substituting all of that here, we know that this is going to be the integral. dE dQ is going to be k dQ divided by r squared multiplied by z divided by r. And this gives us a very similar representation to the ones we had before. The integral of k z divided by r to the 3 dq. We've already know the representation of dq over here that we had from the differential using sigma. So we're going to have kz times 2 pi sigma x dx divided by r to the 3. Lastly, organizing this, we're going to have the integral of 2 pi k sigma z x dx. And we're going to substitute the square root of x squared plus z squared. And all of this is elevated to the 3. And lastly, what are the things that are constant that I can remove from the integral?
Okay.
K,
Pi, 2 pi,
Sigma.
sigma.
2, correct, 2 pi k sigma, actually z. X isn't constant because x is what we're varying. So x is going to go from 0 to r. Okay, so x is going to be a variable. So this is going to be the integral of x dx divided by x squared plus z squared to the 3 halves. And that would be the integral we need to solve. Okay. And the procedure to solve that integral is very similar to the one that Enya walked us through last time. the screenshot. Oops. Very similar to the procedure that, it's actually the same procedure, just that we've got an X here on top. Okay. Okay, we're not gonna have enough time to solve the integral, but that is gonna be in the video. We're gonna do that, so.